This is the ROS Developers Podcast, episode 75.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo Tellez from The Construct, and today I would like to dedicate this episode to all of those people that enroll into the ROS system in order to create their own humanoid robots. Right? This is your dream, right? So you were inspired by the movies where the humanoid robots played a very important role, and probably as me. So I am the freak also of this area. So I was also inspired. So if that was your case, and then you decided to start learning ROS and robotics in order to build the best humanoid robot of the world, then this episode is dedicated to you. And today, actually, we are going to talk about bipeds, and bipeds that use ROS and that are used with ROS for robotic locomotion. But before going into that, let me remind you about our ROS Online Academy. Yes, at The Construct, we have created an online academy named the Robot Ignite Academy, which contains a ROS learning path for beginners. So you can start by learning Linux and Python for robotics, and then you can continue learning all the basic ROS concepts required to become a ROS developer. And then we conclude with a course that teaches you how to build your own robot and how to ROSify it. Then have a look at the link I'm going to put on the show notes. Really, it's a very, very nice path to become a ROS developer. And now let's go to the subject of today. So let me introduce you Luis Sentis. Luis is an associate professor in aerospace engineering at the University of Austin in Texas. He also holds a PhD from Stanford about humanoid robots. So you can feel the subject that we are going to talk today, right? He is also the founder of a company called Apptronik Systems, and he's the member of the board. So Apptronik is a company developing actuators and controllers for robots, and for robots with high power and high efficiency. And they are about to launch, this company, their latest product, which is called the Draco bipedal platform. And this robot is a humanoid robot, torso, let's say, that relies on their actuators and controllers. So let's learn more about this subject with Luis. So welcome to the podcast, Luis.
Thank you, Ricardo. It's a pleasure to be here.
Our pleasure, of course. And you are in Texas, but you are also from Barcelona, right?
That is right. I grew up, all my family is from Barcelona, so I'm kind of an outlier on coming to the US. I studied in the UPC, the Polytechnic University of Catalonia, and that was back in 1995. Then I worked for a year in the City Hall in Barcelona, and finally I went to Silicon Valley and worked for a couple of years in 96. And continue on with the graduate studies and a PhD ultimately in robotics at Stanford. So almost 26 years almost here 25 years in the US.
In the States, right? Impressive. And then now you are in Texas, in a different place, teaching at the University of Austin and doing research, right?
Absolutely. I spent about 14 years in Bay Area. Part of it working in companies, and then later on going for an academic life and doing, grad studies, but then also I became a researcher at Stanford for a few years. And then finally, I look for faculty positions, and turns out my wife is also faculty. So we are what is called the dual body problem, that you have to find two faculty positions in the same place, and it's awfully difficult, to be honest. So the place where we settled is here in Austin. Is a wonderful city that you come here, come to see me, please.
Okay. Okay. Yes, I hear that a lot of startups, they are moving actually from the valley, from Silicon Valley to Texas, to Austin, also specifically to the city of Austin, and that's the place where you have founded Apptronik Systems, that the company that is building this Draco robot. So can you explain to the audience what is Draco?
Yes, absolutely. Draco is one of the pivoting programs in the company Apptronik. Apptronik is divided into two sections. It has something called Apptronik Labs, and then it has Apptronik Commercial. Apptronik Labs is really where the fun happens, where the concept projects happen, where the most risk-taking projects take place, and that's development of from very high performance actuators that perhaps are under development, under study and characterization for a while. This belongs to Apptronik Labs. But then the humanoid program, there's a humanoid / avatar program. It falls in the Apptronik Labs section. And as well, we have also an exoskeleton program where we develop especially lower body exoskeletons for augmentation, work augmentation. And both the humanoid program and the exoskeleton program, they leverage a lot of the actuator and controller and low level and and as well as ROS, obviously, not to miss it, developments. And then some of these developments ultimately make it to become products, right? We, for instance, we sell actuators as a product. We sell controllers, we sell amplifiers. And nowadays, we are starting selling as a product, upper body humanoid torsos, not lower body. Draco, you might think that it's only the lower body, but it's not. It's actually the lower body and the upper body. So we've had demand on selling the upper body these days.
Okay, but when you mention the upper body, you mean the torso with the arms and the hands and the head? Is that?
Absolutely. So
Okay,
that is not shown in the website. It's under stealth still, but there is a product of a dual arm upper torso that is per request that can be you can obtain all the specs and the prices as well.
Okay. So then this is for the audience. So in case that you are interested on the torsos, that the upper bodies of the humanoids that they are developing, you can contact Luis. I'm going to put contact details to LinkedIn for Luis in the show notes, so you can contact him and ask for, of course, for quotes and so on. But let's talk a little bit more about Draco, because it's the subject that I contact you in the first place and the one that it captured my attention. Can you tell us its main features?
Right. So Draco is a project that started about 2.5 years ago, and it really leveraged what was unique about technology that had been developed between the University of Texas, where I operate as a faculty, and as well as Apptronik. And there was back in those times there was a lot of synergies, well, continue being synergies, but then more at that time between the technology developed between the university. This is a perfect case of what is developed in the university and then how it's copyrighted and how it's disclosed, and then it goes to the company and then it's further developed. In this case, it was really the liquid cool viscoelastic actuators. If you are in the actuation communities, liquid cool has been used often for obvious reasons, for mitigating thermal problems, and then allowing to reach regimes of operation of higher power without demagnetizing or burning the windings. And in this case, we miniaturize it to the level of these motors that are as small as possible for the needs that we have. and as well as the use of viscoelastic, which is a replacement for metal springs that are used in a CS, in shear elastic actuators. So we know some of the good properties of elastic materials is the shock absorption, and also they are pretty good filters for measuring forces. So viscoelastic has additional properties because it has a damping, it's a natural viscous damping. And that, in terms of if you're in the real-time control and the fact that the robots they operate at very high servo rates for reasons that we can talk, but definitely natural damping, the friction, the known friction of environment, it plays to the advantage, especially if you're interested in doing position control, right? And it turns out that locomotion, it does benefit by position bandwidth, but something called position bandwidth allows you to basically move very quick. That allows you foot recovery, but also very precisely landing the foot in the right place, right? So it turns out that using natural damping like viscoelastic actuators allow you to achieve walking that is more robust. This is something that definitely we like to have. So this is the sort of the concept of Draco to exploit this discovery we had on using some materials and using liquid cooling as well, and then turning this into a useful bipedal robot, right? So I can continue on, but I don't want to. If you have questions, I want to pause for a second.
Yeah, sure, no problem. So I was trying to process all the information because also you have already answered some of my questions that I already have prepared for that. So let me just summarize very quickly. So you have developed those actuators which have two very, very specific characteristics that are different from other types. The first one is that they are liquid cooled. And the second one is that they are viscoelastic actuators. And both things, they allow you to provide so special characteristics to those actuators so that they can perform in high-powered and high control situations that are required in humanoid robots. So more or less
that is correct. There's a third quality of the actuators. They have what is called, they are linear actuators basically. And what we do is we have a piston-like drive. This is a ball screw. The motor is still rotary. It's an in-runner rotary motor. It turns a ball nut, which turns a ball screw that operates as a piston-like drive. This was a disclosure that we did back in 2014, 2013. And that allows much more efficiency of the actuators. And also, obviously, you don't have to use harmonic drives or cyclodal drives or other drives that are expensive, and sometimes they have an awful amount of friction, if you will, right? So it's really these three technologies, right? The liquid cooling, the viscoelastic, and the piston-like linear actuation that makes this actuator more back drivable, higher position bandwidth, and obviously a good measure of forces and a good shock absorption.
Amazing. Super cool. This is super cool. And then I would like you to clarify to the audience. So you are using liquid cooled actuators in order to prevent those problems that you mentioned about the heating and also prevent and losing this magnetic coupling, right?
That's correct.
Yeah. Then so if that is so cool, then why don't we have more actuators which are based on liquid cool? So what are the problems when using liquid cool actuators? Is it a problem of control? Is it a problem of fitting everything inside a small package? So what?
You are right on point. All of this is right. There is obviously having liquid cooling adds technological complexity. And that's difficult to, humanoid robots are already some of the most difficult robots to build with many degrees of freedom. Adding first of all the hoses for carrying and all the pipes for carrying the liquid cooling is a difficult process. You need an extra pump. Pumps, you don't have to design it yourself. They're off the shelf, especially from the video game industry. When you build your own PC with liquid cooling, you can get those, but certainly there's an integration step. And then you cannot buy small size liquid cooling actuators easily. So you have to design your own housing. This means that you have to do a whole study on the thermal properties of different motors, the type of electrical motors that are out there, and then design the housing itself and seal it. And then there are problems that belong to the area of fluid dynamics, that they're fluid flowing, and depending on the flow and the speed and the density, there can be problems from leakages to currents. It's called eddy currents that are loss currents. And so it requires more further technological advancements in all those domains, and not everybody wants to go through this process, obviously.
I understand. And can you give us a hint about how did you solve all those problems? So did you design the whole thing completely? Well, you mentioned that the pumps, you bought the pumps from, but all the rest of the things, so it's something that is based on your research, is some technology that is already there, but you have reduced it. Can you give us some ideas about how you solve those problems?
Right. So this was the ideas on liquid cooling and viscoelastic that were developed at the university right by the time that the company was being created, and it turns out that the co-founder of the company with me is my former PhD and postdoc student, Nick Payne, that he worked very heavily on actuation, all sorts of discoveries for actuation. So the bottom line here is that the design of the liquid cooling components were done as part of a grant from the U.S. government for advancing robotics, and then it was disclosed under the University of Texas, and that technology then, once it was developed, it went to the company. The company licensed the technology and now is using it for developing its line of humanoid. So yeah, indeed, it had to be developed somewhere in between the university and the company.
Okay, so maybe the people who is more interested on knowing how it works, apart from contacting you directly, so they can, for example, read some of those research papers that you have created, you and Nick. You mentioned Nick, right? Nick Payne.
Yeah, Nick Payne is the brain behind the detailed mechanical and mechatronic technology. And then he and I, we developed the technology, but definitely Nick is an incredible reference for contacting the technology. Then there's more to that because there's the mechanics and there's the controls as well. So we have published multiple papers either on materials and the efficiency and the power enhancements with liquid cooling. That's published in. If you go to our website, you will find ICRA and also transactions on mechatronics, as well as the integration of multiple liquid cooling actuators into robotic systems. That's also published in transactions in mechatronics at IEEE. And we were very surprised because this year, just a few months ago, they sent me an email that Transaction Mechatronics, they have given us the Best Paper Award for 2018. In 2020, they gave the Best Paper Award for 2018. They are a couple of years behind on the liquid cooling technology. So it definitely caught some eyes, and we're really proud of that technology.
Yeah, I saw that news about your prize. So congratulations, Luis. Congratulations. Very, very good. Very, very tough work and very well done. Congratulations. And
Thank you.
Then I will put also a link in the show notes to your publications page, because I have seen when I was doing the research for this interview, I saw on your webpage that you have a list of those publications talking about the liquid cooled actuators and so on. So the audience can go and read your papers for more information. And another question is how is all this powered? So especially inside Draco. Okay, so you have how many degrees of freedom has Draco? 7,
Well, so the version that is 10. It's 10 degrees of freedom.
10.
Five per leg. That's the version that we are now building. So the version is called Draco 2.
Okay.
Now we're building Draco 3, and Draco 3 is a full humanoid robot that is set to be public in January 2021. Okay. So it's that is a full humanoid. So it has 12 degrees of freedom legs, and it has another 15 degrees of freedom torso. So it's more of a full-fledged humanoid. But right now Draco 2, the one you're talking about, has 10 degrees of freedom with 2 legs.
Okay, and how is it powered? So does it has a battery on top as well as the pumping system for the cooling system? So how does
right? Work? So that's a very good point. So Draco 2 is a prototype designed for research on advanced locomotion. So power it comes from outside. It's not on board. And then it runs through a hose that is connected to the back of the robot. We've done that multiple times. We did that with when we had the Mecha. We still have it, the Mecha Mercury robots, and it's good for advancing research. Of course, is not the end goal when you deploy into real environments. You might know that we also do a lot of research with Valkyrie, for instance.
Yes.
So actually, yeah. My lab actually is known for software more than for hardware. It turns out that we had this period of developing actuators for a while, but then we do a lot of experiments as well with Valkyrie, which is a great machine as well.
Okay, but then Valkyrie, as far as I know, okay, not an expert, it looks to me that has a complete technology, different technology than yours, right?
Yes, yes and no, right? It's still using electric actuators rather than hydraulic. But you're right. It uses harmonic drives. Not all the joint, by the way. So actually, Valkyrie it has our actuators inside. Some of them are our actuators. The calf actuators and the torso actuators are actually ball screw actuators. It has a mix of. So there is overlap between the technology of Draco in the linear kind of sliding kind of actuators with respect to not a sliding ball screw and between Draco and Valkyrie.
Okay. I see. Then, just linking with the last question I asked you about the powered and so on. So it's the Draco bipedal robot. Then it has a set of cables that are the ones that provide the power and also the pressure, maybe for the liquid system, or the liquid system is integrated on board.
It is on board. The liquid system is fully on board. If you open the top of the robot, it has this container that has this liquid this green goo liquid that
like in the movies,
like in the movies, exactly, right? Like Back to the Future. So it's on board. It's very compact, and then it feeds from a DC voltage source that comes from the external power. So that's no brainer. So the power comes from outside, basically feeds all of the amplifiers, all of the comms, all of the sensors, plus the pump itself, and the logic for running the pump as well.
Okay, and then what about the control? So do you have a computer that is in charge of controlling or running the walking algorithms, let's say? And is that computer on board or is also outside? For Draco version 2, okay? So we are talking about that one.
Yeah. We're right now in Draco 2. I know. So and Draco 3 is significantly different. But Draco 2 it runs we run an i5, an Intel i5
Okay.
CPU, and actually right now is a fairly small computer for whole body control. And that's not it because as the demands for other components for manipulation and locomotion are needed, then computers are growing, obviously. But then right now we run really a tiny box like i5, and then it has RT preempt, and then we run the bus actually is EtherCAT.
Ethercard, that was another question. And at which rate are you running there? The control loop?
Right. So the control rate at the PC level is about the classical 1 kilohertz, which
Okay.
it can be discussed in great depth. If you're doing the feedback control loops, which whole body control does it at the Cartesian level, at the PC level, right? 1 kilohertz is falls short. So you really wanna increase the servo rates. But you're going to see strategies where part of the whole body controllers run on a central PC, and then part of it runs at the amplifier level. Basically, amplifiers which do also impedance control or do damping control or do some control strategy at the low level, right? Those run those sync up with whole body controllers, and those run their own servo rates, and those servo rates are much faster. So because
Yeah.
they are at the beta level, right? They can be
Yeah.
from 3 or 4 kilohertz to 20 kilohertz, depending on the company. In our case, I think we're more in the 3 kilohertz realm, right? So I think that you have to see the servo rates and divide it into these two technical structures.
Yeah. I think that also that makes a lot more sense, and it's equivalent to the humans system of control, because we also have those central pattern generators which are producing the signals for walking and for coordinating the movements, which are close to the joints in the spine, so they are not on the brain itself. And then your system of control it looks to me at least closer to that mechanism. So the big computer i5, it's running at 1 kilohertz, but then the other amplifiers, they are running at a much faster and a closer position to the joints themselves, right?
Absolutely, and there is definitely similarities between the biological counterparts and the human motor system, and the cerebellum playing a role as a feedback mechanism at slower rates, and the spinal cord that and those are good analogies that we are all extremely motivated on this kind of biologically inspired robotics and embedded systems. As a matter of fact, by the way, the low-level controllers, the EtherCAT master, we call it Synapse, and the amplifiers we call them Axon.
Okay.
And then the root control board we call it Medulla. So we use actually analogies with the nervous system of the human body.
Exactly.
Absolutely.
Yeah, you're even closer than I thought. So to the human nervous system, even closer. Very good. And you also were mentioning, because you are mentioning a lot of interesting stuff, and your information is packed. Okay, so you're providing a lot of information. Let me try to put a little bit for the audience. Okay, because in our audience we have all levels of engineering and ROS developers. So let me ask you this question. So what is the whole body control system that you mentioned? That's a very important point. Can you describe this to the audience?
Right. So right now we are running a whole body control stack that we call it PNC. P as in Panama, N and C as in controller. So PNC stands for planning and control.
Okay.
It is based so whole body controllers that are based on inverse dynamics as opposed to inverse kinematics have been around since the early 2000s. Actually, myself and my former advisor at Stanford, Usama Khatib, and then one of my lab colleagues, Jehon Park, we are the co-founders of the field of whole body control. So if you go to the root, we are the founders of that field in an inverse dynamic sense. And so what whole body controllers they are really optimizers or feedback control mechanisms that they follow trajectories at the task level, if you will. And they're based on multiple things. First of all, they use what is called floating base dynamics. So this means that the robot it has conservation of angular and linear momentum because it's floating in space, unless there's contact, right? When there's contact, then that's partially broken because there's still some level of conservation of momenta, but that's included as part of the definition of whole body control. And then there is tasks which are cost functions that need to be fulfilled in Cartesian space, and there is constraints, and constraints are different types, right? There is contact constraints, those exerted by the feet and arms and other body parts in contact, and there is also either equality or inequality constraints dealing with kinematic constraints, and then with dealing with other requirements that you need that are required for running your operation. They also are normally organized in terms of priorities, in the sense that all the whole body controllers don't rely on trajectory generation algorithms, on whole body trajectory generation. They rely on simplified models. You design a trajectory, like for instance, inverted pendulum control. Well, an inverted pendulum is not a humanoid robot; it's an approximation. Therefore, the trajectories that you compute with inverted pendulum planners might not be feasible with a whole body controller, right?
Okay.
And then the same happens with the trajectory of the arms. The arms, if you only consider it a point in the Cartesian space, then that trajectory is not necessarily feasible, right? So whole body controller bypasses the need for checking for feasibility, and then directly executes the trajectories. And then what it does is that when they conflict, because they conflict often, right? Then it just prioritizes some trajectory over others. So that was a quick way back when computational was short and it was very difficult to create whole body trajectories. And it brought a lot of the success that we see in all of the humanoid robotic community today, especially with impact in the DARPA Robotics Challenge. Nowadays, it is starting to be possible to design whole body optimal trajectories or non-optimal trajectories, but feasible trajectories, certainly based on inverse kinematics, but also based on trying to be also in dynamic based trajectories as well. So we're starting seeing a blurring of whole body controllers and motion planners as well.
Okay, and do you provide any implementation of this? For example, do you know about the OpenSOT implementation of the whole body control system? Is that something based on your research, the OpenSOT, or vice versa? So you have developed from OpenSOT. So I don't know really.
Well, we've always developed our own whole body controllers since we studied the field many years ago. So and OpenSOT, Enrico Mingo and IIT crowd, they are great friends of mine, and we talk often. We have synergy. We organize workshops, and so there is definitely a part of the community. They do have their own style of doing whole body control, using weights and there's a lot of whole body controllers today. Our flavor, we call it hierarchical whole body controller, and that's developed by ourselves. It's the PNC, which is a software stack. It contains many services and state machines and so on, but then it contains as well a core whole body controller called IHWBC, which is different than OpenSOT. So different properties, more focus on the use of inverse dynamics, more focus on achieving higher bandwidth, for locomotion. But I don't want to criticize any particular algorithm. I think that the ones that are out there, they are all fantastic algorithms.
Yes, each one is providing one aspect or more focusing on one aspect than on another. Just wanted to know the relation on so that's great. So then let me go, because we have been talking a lot about the Draco and how it works, the actuators, the controllers, etc. But yeah, I mean, this is the ROS Developers Podcast. So where is ROS here? So how can we program this robot with ROS?
So it's a very good question. I'll tell you where ROS is, and then I'll tell you how to program these robots with ROS. So ROS is being used as a middleware, obviously, and in particular as for real time communications. We know ROS until recently didn't provide facilities for real time, but then recently we have facilities for real time memory sharing and process and multi-threading. And one of them is Node-RED. So those of you using Node-RED, the whole body control, the PNC, our software stack for whole body control, and then also the Apptronik embedded software stack is based on Node-RED processes that they handle, for instance, the Ether master communication for real-time communication with all embedded systems that runs in a Node-RED process, and then PNC runs, and the servos, they run in another Node-RED, and then there's other processes. So rather than using TCP/IP communications for multi-process, we use this multi-threaded facility of ROS. So that's one of the answers.
Okay.
Do you want to ask more questions, or do you want me to continue on?
Yeah, sure. So if my question was, next one was about ROS 1 and ROS 2, which one was? But if you mentioned Node-RED, which is based, then it's ROS 1 for sure. Because it doesn't exist in ROS 2. And do you achieve to have the control in real time based on ROS? Or, I mean, ROS is used as a higher level system, like a mission planning system. You know, that the one that says go to this position, but then is beneath this go to the position, there is a controller that actually moves and computes the trajectories of each one of the joints and sends those commands to the joints, and maybe those are not running ROS.
Right. All of those are part of what PNC. PNC has all the logic for the statement. You're right. We don't run state machines from ROS, and then we don't run any of the control packages for ROS because we are focusing on higher servo performance, if you will, right? So those processes, the state machines, and the planners for locomotion, and the feedback loops, they run within a Node-RED, which is a part of a ROS infrastructure. But then we're not using really ROS calls for running those processes. I think that thinking now loud here, high performance locomotion, like Raver style locomotion or dynamic locomotion, has not really made an entry in ROS.
Yeah, that's right.
And that's the main reason, right? And now you're mentioning it would be an opportunity for us to make a contribution to the ROS community with dynamic locomotion. Maybe we will contemplate that possibility.
Yeah, well, there is a project which is called Micro ROS. Are you aware of that one? Which is about putting ROS in microcontrollers, and then it would also apply, I think, to control boards for joints. So that in that case, you are bringing the topic of ROS to the joint, to the controller itself, and then I think that in that case, that would be possible to have it because they are also having real time working, so they work in real time. And maybe that's a possibility. I don't know.
I think it's yeah. I'm familiar with the
Project?
capability and I think it's a great idea and the ROS developers they are really understanding the needs for the low level controls
Mm.
engineer. I think that the one of the reasons that it's taking a little bit longer to be adopted is that there is a particular culture from embedded system engineers that there is a great deal of care on the buses at the low level, on all the processes going down there that they want to have full control, and they have their own sort of already facilities for achieving the highest possible performance, but then at the cost at the same time of less introspection because ROS topics is very powerful, and then if you don't have ROS topics at the low level, then you have to introspect with your own facilities. So
Yeah.
there's definitely synergies that I think are going to occur between the ROS community and the embedded systems community. Absolutely.
Okay, let's go for the final question because the alarms are starting to ring, and I understand. So we have been here for already 40 minutes. So my final question is, what are the plans for Draco? So you already mentioned a little bit about Draco 3 and so on. So can you give us more details about that?
Yes, absolutely. So there are many different plans, but the main plan is really focusing on legged manipulation. So at least from my point of view, humanoids are systems for manipulating the environment, for operating in home environments, in construction environments, in logistic environments, but we focus on the arm manipulation. So the legs are there to walk to the place,
Mm-hmm.
to move in the difficult flatter environments, but they are kind of a secondary type of task. I know it sounds that it's not, and the main reason is because locomotion is very, very difficult, and especially
Yeah.
with small feet, and so it has taken a lot of priority over the years. But it looks like the community we're starting to approach the point where locomotion is starting to be really robust, and then I'm expecting that in the next couple of years we're going to see advancements on estimation, advances on precisely precision of the leg movement, and advancements on algorithms and sort of model predictive control algorithms that they will make bipedal locomotion much more robust than it is today, and therefore now the problem becomes a manipulation problem. So the objective is to grow the manipulation capabilities to be able to easily tell robots what to do. It's difficult for dual arm bipedal robots what to do, but there is clear advancements on technologies from the use of affordances, and we've seen that on demos that we've done ourselves with NASA, for instance, on being able to using affordance templates to be able to manipulate long-term mission tasks, like we did a task of a bomb disposal, that we had to remove a bomb, and then that was fully teleoperated in the sense of using affordance templates, but then also the use of dialogue as well for commanding complex missions to humanoids like Draco. The combination of that, we're also going to see learning from demonstration also being implemented in Draco, whether it's kinesthetic teaching, basically grabbing the end effector or pushing the robot and make it walk or move the arms to certain places, or whether it's showing it in video. That also is going to increase the ability of working with these robotic systems. And finally, the thing I want to mention is that also, obviously, the use of augmented reality is becoming every time easier with environments like Unreal and other environments where you can project in a more immersive environment, and also you can use it for collaboration with other robotic systems. So all of these fronts are spawning from this Draco program, and at least from a laboratory standpoint, you're going to see code being developed, and then some of it is ROS code. For instance, new odometry for legged locomotion. That's part of a ROS package that we're designing, and also localization and for humanoids and navigation, obviously for humanoids and other legged robots like quadrupeds, right? All of these are processes that are packages that we are developing within a ROS ecosystem. So you're going to see more legged odometry for ROS for legged robots. You're going to see more localization and more navigation as well for the ROS community happening in places like our lab.
Wow, amazing. That looks like a lot of work. A lot of work, a lot of interesting work. Really, really. Super cool, super cool. So, thank you very much, Luis, for coming to the show. Thanks a lot.
Ricardo, thank you, and hi to everyone. I hope to see you in person or in some conference to the whole ROS developer community. Thank you.
Great, thank you very much. Then, before finishing, I would like to remind you, all the audience there, all the ROS developers there, that our goal on this podcast is to achieve a 10x increase in the number of listeners. So, how can we achieve that? Only with your help, guys. So if you like the podcast, please help us reach that goal. And how you can do it? Simply recommend us to your colleagues and give us 5 stars on iTunes or Stitcher and give us some feedback. Let us know what you think about the podcast. You can do it on the iTunes itself or on the show notes, on the post of the show notes. And that is all for today. See you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.
The ROS developers.